Thank you, organizer, for offering me this great opportunity to talk our work. And it's a work of the 16 students. The paper is published, so you can scan the code if you're interested in. It's big topic. Okay, so let me start to introduce the motivation. And this debate has been going on for 60 years. Everyone here knows. So let me just do a quick survey. If you believe in the Darwin selection theory is true, please raise your hand. Okay, only half you. If you believe the Kimura neutral theory is correct, raise your hand. Okay, you say the debate. Okay, so the one sentence is a survival fittest, increased fitness. And the neutral theory is a survival luckiest. So it's a contradiction. And there's no big data to examine this fundamental issue. But now, because pandemic, we have millions of genome data ready to tackle this problem. And we'll vote again after my talk to say, what's your opinion? For evolution, you have to run the mutation, which is due to the copy error. So here we have the two big assumptions to help us to analyze data. It's a prior assumption. The first one, polymerase don't have a sense position. So every position has the same error rate. Second, because polymerase is a very stable molecule, typical its error rate will not change over time. So it's time independent. We make those two prior assumptions. We also have a tool to determine the mutation is under positive selection or under negative selection or under neutral selection. By looking into the population, counting the observed mutation in the population, we define substitution rates, which are the big C, right? And then we have the default polymerase error rate, mu. I use the same note. Okay, so C over U, very simple. If it's 1, neutral selection. If it's greater than 1, positive selection. Smaller than 1, negative selection. Everyone knows this. Everyone knows this. Okay, so we have the tool, we have data. So now let's look at so we will show you 3 existing theories not able to explain the evolution data of the SARS-CoV-2. And then we propose new theory, which are near-neutral balanced selection theory. It's a hybrid of the near-neutral theory and the selection theory. Let's see. So SARS-CoV-2 is a 30 nucleotide base, and it's coding non-structured protein and structured protein and accessory protein. Okay, 10. And then for the biggest gene is the reading frame 1AB, which coding 16 non-structured protein. Typical is the key enzyme for this one. Okay, so let's look at the data. This not done by me, it's done by NextGen. They did phylogenetic tree kind of analysis, show you the evolution. So pretty much follow what we expected for the selection theory. You have random mutation, it's increased fitness, it's more abundant, just like the Omicron, XBB.1.5, they become dominant species. So looks selection theory is good. However, when you look at this data, problem coming. We experienced a 6th wave of infection, which means the very population fluctuated big. Second, start 2 years ago, 21, we start to have the vaccine. So you have the 1 dose, 2 dose, boost dose. So now we put selection pressure on this virus. Okay, yet this is the counting numbers of mutation over the time. Boom, it's a constant rate, which does not change when we environment change. This makes Darwin selection harder to explain, right? Darwin theory is the environment change. Then you have to respond to that environment change. So you expect it, the substitution rate somehow should be time dependent, so this is hypothetic. This also makes the auto near-neutral theory not look that, because it's dependent on population size or population dramatic change, but rates are constant. Not good. Good for Kimura. Straight line, neutral theory, but I know fraction of the people don't like this one. If this is true, we are here because random come here. In billion years, we go back to bacterial. So let's look at detail. If Kimura theory is suggesting site under negative selection, this is 0 mutation rate. And the site under positive selection, well, it's neutral, so no difference. They should have the same substitution rate, correct? And if you summarize, should be Poisson distribution, right? And the center in the single rate describe that thing. So this is what you should expect. Is the Kimura correct? Let's look at the real data. No, Kimura is not correct. You see, some on the positive selection, some on negative selection. I draw the red line is average mutation rate. It's roughly equal to the polymerase error rate. Not good news for Kimura. Okay, so we can summarize this data use distribution. Everyone here like use distribution. So we sorting by the numbers of mutations, so we can got this so-called L distribution. The X is relative substitution rate. It's very easy to interpret. So C over U is 1, neutral. Greater than 1, positive selection. Smaller than 1, negative selection. So we got this L distribution. Beautiful L distribution. Then we look at the Darwin theory. Darwin theory basically negative selection, positive selection. So you have 2 peak. No, not that positive. Okay, and you look at the Kimura. Kimura basically is a neutral selection, so it's a center on this neutral. No, we don't have that peak in the 1. And Ota theory, it's mostly slightly negative. You don't assume there's slightly positive. So no, we have the slightly positive. So this is our new theory. Near neutral balanced selection theory is a hybrid of the neutral theory and the selection theory. Okay, so we're facing the challenge. How to explain that molecular clock? Well, easy to explain. Because you have some gene under positive selection. You have some gene under negative selection. When that balanced, you calculate the average. It looks like the neutral selection. That's the answer. So it's a balanced selection. And this is the 1AB, remember? It's coding 16 non-structured protein. And you do the analysis. You say some are positive, some are negative. And actually, you can interpret the function. We don't have time. Okay, I'm done. So now, our theory is best to explain the SARS-CoV genomic data. And here, join us to make history. And so you see, that's ending my talk. Thank you so much.
Thank you, Chun. Any question?
If no question, I keep talking. Yes, I keep talking. So
I think we have a question here.
Oh.
Yes, it's true. It's millions of COVID genome data, but it's also kind of hundreds of thousands for humans as well. So how much of this, let's say, balance selection, like I would say is like asymmetric selection, maybe, in other big data sets? Have you tried?
Okay, good idea. So far, this only examining for the SARS-CoV-2, and we use a select genome. So it's a 15,000 genome. It's selected by NextGen team. And so we start to examine the other species, flu, HIV, and monkeypox, bacterial, plant, animal. So that's why we need people to examine those genomic data, use this new theory. And the hallmark of this new theory is very simple. We should expect the L distribution, one hallmark. Second, we should see the balance selection. I don't want to take more time, so I think the next